When will we see another Earth? That's the holy grail of exoplanet astronomy, right? An Earth-sized world orbiting around a sun-like star in the habitable zone. We really want to be able to see that. And it's not just a factor of the telescopes. A bigger telescope will just make the glare of the star brighter and you still can't see the planet beside it. It's a factor of 10 billion. And so to be able to actually resolve just the planet without the star, you need a technology called a coronagraph. And there are many coronagraphs installed on observatories, both on ground and in space today. But even those really can't take us beyond showing a very large planet orbiting around a dim star. And that's not that other Earth. So today I'm joined by Dr. Lucie Leboulleux. She is an astronomer with the University of Paris, and she specializes in developing coronagraphs. She's working on next generation coronagraphs that hopefully for the future telescopes like the Extremely Large Telescope and maybe LUVOIR be able to resolve and block that light. And the technologies that she's working on are quite exciting. I've never heard some of this stuff before, and yet people are dreaming this stuff up. Now, I want to warn you, she is French and has a French accent, and so you may have a difficult time being able to understand what she says, but I promise, tough it out. It will feel very natural after a while, and the things that she says, the technology that she's working on, I promise you have never heard this before. So it's a fairly advanced conversation, and yet if you want to really stay abreast of the state of the art, I think you're going to take away a lot of information from this interview. All right, enjoy the interview. So where are you located right now?
Right now, I'm at the Institute of Planetology and Astrophysics of Grenoble in France, in the Alps.
And before we started, we were going to talk about coronagraphs today, and you went and found a coronagraph and brought it as. Can you show this?
Yeah. So this is actually two chronographs. I don't know if you can see with the gray background here.
Yeah,
and those
absolutely.
Are designed for the extremely large telescope. So the telescope that is being built currently in Chile, in the Atacama Desert, and it will be a 40-meter diameter telescope.
Oh, that's
this will be planet.
and I can't believe it's so small. I mean, for people who are listening for the podcast, the actual coronagraph is like maybe the size of a silver dollar, or in Canada, a toonie. It's not a very big thing. And what's going on inside that object?
So inside that object, what is going on? So here you can I don't know if you can see.
Yeah.
There is a part of light that can go through and a part of the light that is stopped. And the idea is to modify the wavefront. So it's so the image of a star doesn't look like a point or a classical airy pattern like we used to have using telescopes. We have no stellar residuals in a large region around the star. And if we have no stellar residuals, we can detect very faint objects. We can get photons from other objects in this area.
So this is the challenge, is that like what we all want is to see a picture of a planet.
Yeah.
But the problem is that the planet is like an Earth-sized world around a sun-like star. It's something like 1 billion times fainter than the star.
Yeah. So another Earth around a star that looks like our sun would be like 10 billions times fainter than the star.
Right. Oh, a million. Yeah.
Yeah.
And so if you just pointed any telescope, the star and the planet are going to be in the same field of view. And so you just can't resolve the planet apart from the star.
They are too short, too close to each other, and also the planet will be totally lost in the stellar residuals, in all the speckles, all the photon lost from the star. So the planet is somewhere, but we cannot detect it.
And even if you had a telescope with infinite magnification, is it still like there's just too much like dust around the star, that there's too much glare coming? Like could you zoom in right on the planet, or are you always going to have this problem?
So except if we have an infinite diameter telescope, we have a problem. The perfect telescope will be infinite and totally flat, totally with no errors, no surface error. But our telescopes are not like that. They are 8-meter diameter telescope. They are like 50 meters diameter telescope, and that's a problem already.
Right. So until we develop the infinite telescope, we need to figure out some way to block the light from the star.
Yeah.
Yeah. And so this is the technology of coronagraphs. So where did this idea come from? What is the history of the coronagraph?
So actually, chronographs were not designed originally to image Earth-like planets or exoplanets. Chronographs were designed to look at the corona, so the area around the sun. So all the wind and all the gas and matter ejections around the sun. And the problem was that they were too faint compared to the sun itself. So Bernard Lyot, a French astronomer, decided to put a mask in front of the size of the sun, and to block all the light, all the photons coming from the core of the sun, and we could look at what is around it. And then later on, we decided to use that technology to look at exoplanets, so planets very faint, very close to their star, like what is happening around the sun. Exactly.
But with the sun, the sun is like the size of the moon in the sky. Yeah. They're exactly the same. That's how we get eclipses. And so it is a disk. And so it does make sense that you can put a disk in front of the sun and see those fainter objects around. Yeah. But with a star that's really far away, they're all just a single point. So yeah. How do you block a point?
So this is where it's really interesting in my opinion, but I have a passion for that. So what is interesting is that the image of a point through a telescope is not a point. It's actually a pattern, an airy pattern or whatever pattern. We have diffraction effect. Diffraction effect everywhere. And so the image of a point is a disk with other stuff around. We want to remove those other stuff around because they can hide a planet, and we want also to remove the core of the star because it's too much light.
So what is causing that pattern? Is it aberrations on the telescope, or is it something from the laws of physics of light?
So correcting all of that, it's only physics of light. It's every time on your telescope you have an edge. That's why I was talking about infinite telescope. There is no edge. Every time you have an edge on your telescope, you have photons, light that is being lost in all directions. So on your telescope, you have a finite size telescope. So you have light going everywhere on the detector. And also, it's not only the edge of the telescope, it's also when you have a secondary mirror and you have those spiders, those sticks that can hold the secondary mirror. They also put light, diffract light everywhere on the detector. And that's a problem. We have complex apertures, what we call complex apertures, and we have a lot of diffraction. And that diffraction, we want to control it.
Right. So, but this idea that what would be just a point of light on an infinite telescope, on a finite telescope that has secondary mirrors and various other hardware, that point turns into a shape, a blob on in your image, no matter what. There's no way to resolve it down to a point. And I guess people are very familiar now with Webb, where it has that 6-point star coming off of it. The Hubble one has 4. That is the shape of the star. And so that, whatever that shape is, that is what you're looking to cancel, not just a point. You need to get rid of that whole shape.
Yeah. You want to control both, actually. You want to control the core of the star because we don't have detectors that can get that much light from a star, and also that few photons coming from the planet. So we want to remove the core of the image, and we also want to remove those artifacts, all those patterns everywhere. We want to control both.
Right. And like at the scales that you're working with, does the wavelength of the light, like almost like the quantum effect of the light itself, is that playing a fairly large role, like the actual waves in your telescope?
The waves, the coming waves?
Yeah, that are coming into the telescope, and from all the individual photons, are they like forming a pattern that matches the wavelength of the light?
So it has different kind of impacts. First, it's a bit complex to explain, but a wave is like a complex number. There is the amplitude and there is a phase of the complex number. And also, when you have these patterns, this diffraction effect, this is due to the amplitude part that is being transformed, and also due to errors, for instance, in manufacturing the mirror and all of that, you also have phase errors. You have both errors in your system. You want to be able to control both the amplitude and the phase of what is arriving on your telescope. And that is really complex. With the chronograph, we can focus on both. We mainly focus on the amplitude effect. We neglect what is happening in the phase often, but now it's changing. We are starting to have very good chronographs. So
yeah, well, and I want to talk about that for sure. So then a coronagraph for a star, what does it look like? Like, what is the actual device? I mean, you have an example of it here, but just like what are the parts that are coming together to make this do its job to block that light?
What are the devices in the chronographs?
Yeah. Like, what is actually happening to the light? The light is coming in from the telescope. What are you doing to the light?
So the light will meet up to three devices. So the first one could be these devices, and it only modifies the amplitude of what is arriving of the wave or the wavefront. So this one modifies the amplitude, but other devices can also modify the phase. Then you have a second. We focus the light on the focal plane, focal plane, where we could have a detector, but for a chronograph, we don't have the detector. We have what we call the focal plane mask. So this is just a disk, which can once again be amplitude disk. So we just block the photons, or we can have a phase device. It's a bit more complex, and we block the core of the star. And then we have another device that is optically conjugated to the first one to remove the residuals that are due to the focal plane mask. So we have up to three devices. The first chronograph that was invented by Bernard Liot only had the last two devices, so the focal plane mask and what we call the Liot mask. And now we start to use those extra components, and they are really efficient to put before the rest of the chronograph, and are really efficient, and we call them apodizers. And so we have up to three.
Now, I'm going to apologize because I don't exactly know what I'm talking about, but I know that this is somehow involved. But don't you use the light and have it interfere with itself to help block out some of that residual?
Yeah. So in optics, everything can be interference. So, but this is actually a way of seeing that. The focal plane mask, for instance, the very tiny mask that we put in the middle, the second component, can act as an interference device, and then we can remove we have a destructive interference pattern in the focal in the detector plane, so the last focal plane, and this is where we will look for exoplanets.
Right.
We have destructive interferences from the star itself, we can see what is behind them, what is hidden.
Right. So you take the light from the star, which is very bright, and you are passing it through this series of filters and coronagraphs, and you're also using that light against itself. You're interfering the light with itself, and the waves cancel each other out, and that leaves you, whatever remains is the planet that is nearby.
Yeah, so we still have residuals from the star always.
Right.
We can, except if we remove all the light, we cannot have no light coming from the star. Coming from the star, we always have. The question is, how can we have as little light as possible, as little photons as possible coming from the star? In particular, in the planet location where we expect to get it.
And what is the biggest, or like, what is the most powerful coronagraph that's operating today?
So today, it's a bit of a complex question because we have chronographs both on the ground, on space currently. We have, for instance, chronographs on the James Webb Space Telescope. We have chronographs on Hubble. We have chronographs on the ground. So in theory, the most powerful ones are, I would say, from the on the ground. I would say in Chile, we have on the Very Large Telescope, we have the SPHERE instrument, which is an exoplanet imager, one of the most powerful today. We also have another one in Chile that is called GPI. It's located on the Gemini South Telescope in Chile. I would say also as instrument Skexeo, which is in Hawaii on the Subaru telescope. So we have several very powerful chronographs today. But I would say some of these technologies start to be old, in particular the one we send in space, because they were manufactured 10 to
20
30
years ago.
Yeah. Many years ago. So the coming generation of chronographs will be really more efficient. And currently, the most powerful chronographs are the ones tested in laboratories on test beds.
Right. So let's talk about some existing instruments right now. So like on the Very Large Telescope, the SPHERE instrument, and I've seen many images from the SPHERE instrument. I mean, that's where we see new planets forming around other stars, newly forming stars. It's quite amazing because you're seeing the planet, but it's a very special condition. It's a young star. The star is not very hot, so it's not putting out a lot of radiation. The planet is very big. It's very far from its star in many cases. And so it is a lot brighter than, say, the Earth would be. What are the limits to those coronagraphs, like SPHERE? Like, what is the most, like, what is it possible to see with SPHERE?
So currently, with all the three instruments I talked about, actually, including SPHERE, we can image a big Jupiter-like planet, I would say. Quite, I would say that a big hot Jupiter.
Yeah. Around it, but it also has to be around a new star that isn't very bright yet. Yeah.
It has to be like, it can be around a brown dwarf or something like that. Also, and we cannot. We are not ready to see an Earth-like planet. We start to have the technology, but it's not the telescope yet, and it will probably be really hard to see it from the ground also.
Right. And Webb is a little better than that, but essentially in the same kind of ability.
Yeah, James Webb, I think there is only one set of images that was released so far. I don't remember. It's IP something. I don't remember what kind of planet it is. James Webb will not be able to go also as close as the Earth is to the Sun.
Of course. Yeah. Yeah. No, you're right. They released an image about a month ago.
Yeah.
Showing one of these I forget which one. I know it was like a bunch of numbers as the name of the star, but it's another one of these, this one with where you've got this newly forming star with the large Jupiter orbiting around it, and it's a picture of a planet.
So that's what so on that image, if you have the image in mind, you don't see the star. The star has been represented with a small 5-peak star pattern, but that has been added numerically, and you only see the planet. Why? Because there is a chronograph in front of the star. In all chronographic images, you actually don't see the star. Normally, you have a very bright spot just to show, hey, there is a star here, but it has been added by Photoshop or whatever.
Right, because it is gone. Like if there was any light peeking through, you wouldn't be able to see that planet.
Yeah.
All right. So now here's the fun part. What are you working on right now? What is the coronagraph that you have on your test bed that you are working with?
Me personally, or
and your team, and what people are. I mean, definitely you personally, because I think it's really important. You specialize in this and you know a lot about this. So what are you working on?
So in general, in test beds what is being tested on test beds all over the world are chronographs that are either for space and going as deep as possible in terms of contrast. So to really, we are talking about contrast down to, up to 10 billion between the star and the planet. They are trying to get that. Currently, we can get a bit less than 1 billion in terms of contrast, 1 billion factor. So we are quite close to getting there, to have very powerful chronographs. Powerful enough to see the Earth. It has been obtained in the Paris Observatory testbed. It has been obtained in the Caltech testbed, I think. GPL maybe. So a few test beds in the world. So it's really, we are getting there.
And so what does a billion give you? If you can block the light of the star by a factor of 1 billion, what would you be able to see in terms of exoplanets?
1 billion would be a very large Earth-like planet. And there is another factor that I have not talked about earlier, is that the chronograph can get something, but at the end, the full performance cannot be recovered unless we have very strong post-processing techniques. So really, algorithm, and people are really good in doing that now, is that the 10 billion contrast factor we have cannot be obtained unless we have very good algorithm also to process the data that would be obtained on telescopes. That's also really important.
Right, and the both go hand in hand.
Yeah, they work together. Currently, the best images we have, the one on the James Webb Space Telescope, the one we have on Sphere, they include a chronograph, but the chronograph isn't everything. They have a very powerful post-processing techniques that are being applied.
Right.
Yeah.
So the one that you have, the one that you brought, that one is going on the extremely large telescope, or is there another level of technology that's being developed for the extremely large telescope?
There are several technologies that are being developed. This one will be for the extremely large telescope. So there are other very large, not like the very large telescope, but very, very large telescopes that are being built currently. There is a 30-meter telescope which will also have specific technologies. So that's an example of technology. There are also phase apodizers that are being built, also very powerful. There are many different kind of components that are being decided on set up on the extremely large telescope, on the VLT, very large telescope, on the 30-meter telescope, on all telescopes being built currently. And I would say on what I am working on will not be for the coming generation of instruments, will be for the next generation of instruments being that will be maybe installed on the extremely large telescope. It's adaptive chronographs. The problem
adaptive chronograph.
Yeah.
How does that work?
Yeah, that's pretty exciting, actually.
Yeah. Let's talk about it. I mean, I know what adaptive optics are, and I know what coronagraphs are. So what is an adaptive coronagraph?
So it's chronographs are amazing, but they're very sensitive little animals. Very, very sensitive to everything. And every time you have atmospheric turbulence, you have whatever wrong is happening on your telescope, you have whatever problem, the chronograph is really bad. And we like really, really bad. Like on sphere, we are limited by aberrations, by the turbulence, by all of that. Same on GPI, the Gemini South instrument I was talking about, etc. So what I'm working on with a team here and with a team of researchers here is a chronograph that can be adapted. That pattern should be modified. So here we have a certain pattern for a certain kind of conditions. Here we have another pattern for another kind of conditions on scientific targets. What I'm working on is that we have a pattern and we can modify that shape compared to what we want. Yeah.
Huh. So you're able to, I mean, like with adaptive optics, you fire these lasers into the sky, you create these artificial stars that you know what they're supposed to look like, and then you deform the telescope to match the star, the perturbations in the atmosphere to make the star a point again. And you're essentially removing the atmosphere. But with this existing coronagraph, it's just a piece of glass that is stuck with the shape that it has, and so you're limited by that resolution. You're always going to have little bits of the star's light peeking out, and so you're attempting to make the actual shape of the mask change to adapt to the conditions of the sky. Okay, so how? So that sounds hard.
So that I have to say that was not my idea at first. I'm working on that, but it was Alexis Carlotti, another researcher, idea at first. So the idea is to use a matrix of tiny mirrors. So here it's transparent, but it could be a mirror also. Mm-hmm. It could be a mirror with dark spots, the same dark spot, and we have a reflection in instead of a transmission of light.
Yeah.
But so we could use a mirror, and we can use mirrors. It's called a digital micromirror device, DMD. It's a technology that is used in a projection system, and we are trying to use one. So it's a set of tiny mirrors, like 10 microns size of.
But like pixels, but mirrors.
Yeah, and we can move them in one direction or in another, to another one.
You can turn these tiny mirrors that are 10 microns across and angle their shape. Okay.
Yeah. So we can put them in the direction where they reflect light, and we can put them in another direction. So they will just remove the light elsewhere. Mm-hmm. This is how we can get, and we can modify them as much as we want. We can put whatever pattern we want on those mirrors. You want a mirror with the shape of star, actually. If we want a mirror in the shape of a bee, of a herd, or whatever. We can put whatever pattern we want. And if we want, we can put whatever pattern we want. We can put this kind of pattern. We can adapt it to what is wrong on the telescope. We can say, I want actually to follow that planet while it's moving. And we can decrease the starlight around the planet while it's moving and follow the planet motion, which can be also really good when we want to do spectroscopy. If we want to have spectroscopy only like we put a fiber, single mode fiber, and we want to get only the photons of the planet to be able to do spectroscopy and get the chemical composition of its atmosphere and any information we
Right. So then how do you move these tiny little mirrors so quickly?
It's like for the deformer in adaptive optics, we use, like you were mentioning, we want to compensate the turbulence of the atmosphere, the motion of air above the telescope, and we use a deformable mirror. And behind it has small actuators. And we just send a command, like voltages.
Mm-hmm. Right. I mean, it sounds similar. I'm sort of thinking about like a Kindle, like I have a Kindle here, right? Like a book, and it has little black dots inside that can be turned one way or the other with magnetism. So they can be in one form, and then they can be flipped around, and this idea of e-ink. And so they apply a voltage, and it flips over the ones that are necessary and changes the shape that is on the screen. And so I'm kind of imagining something like it's like an e-ink version, but it's a mask that you're using to block the light from the star, but you're dialing it in. And so would you need to I'm assuming you're going to use like a laser, like an adaptive optic system. And so would you have that in the field of view, like right beside the star, or could it be far away from the star, and you could be able to know how to adapt the optic system?
So actually, we will not use, so far, it's on process, under development technology. So far, we are not using a laser, because it should be able to compensate for what is happening inside the telescope. So the laser in adaptive optics aims to correct for what is happening above the telescope. With this kind of tiny mirrors I'm talking about, we want to compensate all errors happening inside the telescope in general.
But I mean, like I could see as soon as light starts to peek in to your instrument, then you compensate to try and get rid of it again. But how do you know you're not getting rid of the planet? Like that's the trick, I think, right? Is that you have to turn this so carefully, and you could remove the light from the planet.
Actually, no.
Oh, really? Okay, great. Yeah. Easy. But it's easy.
Except if we totally block all photons, we cannot remove the light of the planet. What is happening? So that's for the apodizer. So that's for the first mask. Some light is passing through, like we have transmission or we have reflection with the reflection. We have reflections, so we have photons coming from the planet and we have photons coming from the star, but they're not coming with the same angle. And right. Actually, then I told you about a second mask, the focal plane mask, the one that is located at the star location once the light focuses on what should be the detector, but the detector is further. We have that tiny mask that is located just at the star position. And that mask doesn't block the photons coming from the planet. It only blocks the photons coming from the star itself.
Right. Okay. I mean, I sort of think of like maybe almost like focus, like you can just sort of tell when you've got the planet in view, and then you hold it in that position to keep the planet visible. And as soon as you start to lose the image of the planet, then you go back the other way to bring it back into the right level of blocking. So it's not focus, but you're blocking light. So if this becomes operational, what will this give you? What level of star to planet ratio can you get to?
So this way we have tested it. We don't know yet. We don't know fully yet, because also we have many things to implement, to set up on the test bed. Currently, chronographs can go down to a very large Earth-like planet next to a sun-like star. On the test bed, we are more like a large planet next to a sun-like star. So it's a bit different. We need to implement many different things to know more. Actually, from the ground, we don't expect to do so much better than that, because then we also have all those other limitations, like we have the atmospheric turbulence and all of that. So we don't only have. We know we cannot get better than a certain level of performance on the ground looking at like in Chile or in Hawaii or in the Canary Island and all of that. We know that we cannot get better than.
So even with adaptive optics, you really are limited by the atmosphere. To do this right, you want a space telescope.
Yeah.
Yeah. So, I mean, James Webb, for example, is it's an infrared telescope and it has a lot of jobs. It's looking at the beginning of the universe. It's looking at planets. It's looking through into star-forming regions. It's looked at Neptune. Like, it can do all kinds of things. But let's say that you wanted to build a telescope that's only job was to look for Earth-sized exoplanets, and it didn't have to be able to do anything else. What would it look like? What would that space telescope, its only job is to look for Earth-sized planets with a fancy coronagraph? Tell me describe this telescope to me.
So that's really interesting that you're asking this question, because that telescope will happen.
Mm-hmm. Of course.
Yeah, it will happen. And it's so in last November, the NASEM, including NASA and all that, they decided to allocate. So they published a report.
This is the decadal survey, right?
Yeah, that's the decadal survey report. And that decadal survey report decides what will happen, how will be allocated the budget of 2040, what will happen in astronomy in 2030, 2040. Mm-hmm. And the decadal survey is decided to allocate $10 billion to a large space telescope being able to look for Earth-like planets. So this is really good for us astronomers. We're really happy. And what will it look like? It should currently, it has not been decided yet. Currently, it could be a segmented telescope like the James Webb, around the size of the James Webb Space Telescope, so 6-ish meter, a diameter of 6-ish meter. And it will have a very powerful chronograph. And not only, actually, it will have a very powerful chronograph made maybe of patterns like that too. Mm-hmm. So with the three components of the three different components I was talking about, an apodizer like that, a focal plane mask, and another mask behind. And it will also have deformable mirrors. So do you know what it is? Mm-hmm. You work about adaptive optics. Mm-hmm. Deformable mirrors are mirrors you can modify the shape.
And sorry, let me just stop you for 1 second, because I think for a lot of people, the idea of adaptive optics should only be necessary on Earth because you have the atmosphere. So why do you need an adaptive optics system in space when there's no atmosphere?
So very good question. I love these questions. So you need one because first you have residuals, you have errors. Except if you have a perfect telescope, you always have errors. So for instance, you can have a mirror that is not fully flat or curved, depending on what you want. And you have tiny, tiny errors. We think that on that large telescope I was talking about, we want a flatness, a surface flatness of mirrors down to 10 picometers. RMS, 10 picometers. It's
right.
Really, really small.
That's really flat, yeah.
Smaller than an angstrom, so it's really, really small. On a 6-meter telescope. So this is what you want, and that you cannot get. Currently, like the James Webb, it has a flatness performance of a few tenths of nanometers, I think.
Mm-hmm. Yeah. Like 10 nanometers.
Yeah, 30, 40.
Right, yeah.
And so we want to get a factor of 1,000 compared to that. It's huge and it's so small.
You want this level of flatness, but also on a space telescope that you launch from Earth, and the telescope has to deploy a segmented mirror and a line.
Yeah.
That sounds, people were so excited about the accuracy of James Webb. Now you want to do 1,000 times more accurate.
Yeah.
So the adaptive optic system allows you to compensate if it's not perfect.
Yeah.
Right.
You want to compensate, and you want to do more than that. You also want to use the deformable mirror to remove even more starlight in the area you are looking for an exoplanet than what the chronograph is doing. The deformable mirror will be used not only to compensate for aberration, but to work with the chronograph. In addition to the chronograph, to go on removing starlight from those regions.
So it's like you're kicking away the starlight from the mirror as well as and then letting some will get through to the chronograph, and the chronograph gets rid of more.
Yeah.
I understand. Right.
They need to work together, actually. And that's, it will be very beautiful. And before that large telescope coming in 2040,
yeah,
there will be another telescope in 2028, I would say, which is called the Nancy Grace Roman Space Telescope. And it's also a NASA telescope. It's developed now, and it will have a deformable mirror sent in space to do that. It will be a prototype demonstrator telescope. It will be a small telescope the size of Hubble, 2.4 meter diameter, I think. So the size of Hubble, but it will have very powerful technology on it. It will not be able to detect really, or maybe a bit by chance, Earth-like planets, but it will have all those unique, very beautiful components, devices on it to see if they can survive in space.
Right. So it will test. So Nancy Grace Roman will test this technology, this idea of a deformable mirror in space, this next level of advanced coronagraph. I mean, Nancy Grace will be mapping dark energy. It will be discovering exoplanets through microlensing, but it will also be practicing this technology. I didn't realize that it would have this deformable mirror on board. That's really exciting. It's more of a Pathfinder mission for that next generation planet hunter.
We call it a demonstration telescope, because it would be the first time. It will demonstrate the possibility of what will happen on that next large telescope that should be called LUVOIR or LUVEX, still changing. But it's a demonstration telescope.
I mean, I think a lot of people were very excited by LUVOIR, that it would be a maybe 10 meter, maybe 15 meter space telescope. And we're disappointed that now it's probably going to be smaller, that it's, because of the decadal survey, it's going to be maybe the size of Webb. But what makes it exciting again is this chronograph, that it's going to have all of this new technology that is more realistic to build at that smaller level. You take all of the experience gained. I mean, again, Webb was 20 years, $10 billion. Like, I don't think anyone wants to make the mistake of building a dramatically bigger telescope again. But I love this idea that you have Webb for the kind of the hard, proving the deployment side, and then on the other hand, you have Nancy Grace Roman testing all these technologies, and then that comes together for that next level telescope that will do this one job. Although it's not going to do just one job, LUVOIR or whatever it's going to be called. It will be a general purpose instrument.
Yeah, it will look at many things. In particular, one of his main target will be Earth-like planets. We are disappointed it's smaller than what some people were working on, but it's not. It's a good trade-off, I would say, because first we can still detect Earth-like planets at that diameter of telescope, at that for that design. Of course, if we increase the diameter, then we can detect more Earth-like planets, and we would be happy of that. But we still have very good targets to look at and to look for. with that diameter, and also it will not be built as the large one, the 15-meter one was designed, because the 15-meter one was designed as James Webb, meaning a large primary mirror, a small secondary mirror in front of it, all symmetrical. This one will not be symmetrical. It will be off-axis, what we call off-axis. It will be a bit different, so we'll not have that secondary mirror here hiding a part of the primary mirror. I mean, it's smaller, but it's a bit more challenging in terms of techniques of
that idea of off-axis. I've heard this several times. What is exactly like when we think about Webb, we've got the primary mirror, you've got the light is coming in, bouncing off the primary mirror. The secondary mirror is hovering in front of the primary mirror. It's bouncing off of that and then focusing. It's like if you have a telescope, if you have like a Newtonian telescope, you know what this looks like. So What is an off-axis telescope? How does that work?
So an off-axis telescope means that when we have a normal telescope, I mean a parabolic telescope, we use the center of the parabolic mirror. An off-axis telescope, we use another part of the parabola. So the light then focuses, the focus point of the mirror is not in front of the mirror.
I see. So it's focusing the light a little off to the side, and that's where you capture the secondary mirror, and that's where you focus it.
Then you have nothing that hides the primary mirror. So you have less edges. You have less. You don't have spiders in front of the primary mirror. I mean, I don't know how it will be designed, but normally this is the way. This is optimization we are trying to do.
And so when people always complain about the bright stars around Webb or Hubble, in theory, an off-axis mirror won't have any of those diffraction spikes at all. But I'm sure there'll be something in front of the way in some mechanism. But I guess the challenge of the off-axis mirror is that it's much more difficult to grind the shape of the mirror because it's changing. Like when I think about if I want to grind my own parabolic mirror myself, I just have to get a shape, and then I can turn the shape in the glass, and as long as it fits, then I've made my mirror. But if you want one that where the focus is somewhere else, that sounds like a very complicated grinding job.
It's always complicated. Not that much, because actually we just do a large parabola and we cut part of it.
Oh, so you make a much bigger mirror and then you cut the piece out that you want.
Yeah.
Oh, that makes sense. Okay. I thought you had to...
This is the way off-axis parabola are made. For instance, what we use on test beds, we use off-axis parabolic mirrors. And actually polishers polish a very large parabola, and they cut part of it at the right location to get the right inclinations, the right focus point, and all of that. And they cut part of it. And with a large parabola, actually, you can get a bunch like 6 or 4 small.
So you didn't exactly answer my question. So my question was, well, no, it's fine. It's fine. You were very excited to talk about the next telescope that comes after Webb. And, we got Nancy Grace Roman testing the technology, and we've got LUVOIR or whatever it's going to be. But it is a general purpose telescope. One of the things it can do is, in theory, detect Earth-sized worlds around sun-like stars, but it's also designed to do other things. There are compromises. So my question was, what's the perfect machine? If you had no compromises, that you didn't have to worry about someone who looks at nebula or someone who wants to study galaxies wanting to use your Planet Hunter, all it's for is to image planets. What would your dream telescope, coronagraph, what's that mission look like?
So if NASA was ready to give me $10 billion,
no problem. I've already cleared it with them. It's coming.
So I would say it's a space telescope. as large as possible,
Mm-hmm.
At least 6 meter large telescope. I need to think.
You've never thought about this before?
Probably off axis too, because we can really get more photons and we have less drawbacks when building chronographs behind off axis telescope. Yeah, actually, it would be then I would say an adaptive chronograph, because I really believe in the technology of just removing the starlight on one area at the planet location and then putting a single mode fiber, because what we are looking for in terms of exoplanets is images and spectra. And what I would say is a chronograph fully compatible with getting a nice high spectral resolution spectrum of planet at any location of the planet. And that is not done that much today.
So sorry, you say any location of the planet. Do you mean its location in the orbit, or do you mean like looking around at the planet itself?
Like we know where the planet is. I imagine a mission where we know, like with imaging exoplanets, we did discover a few exoplanets, but it's not the main method to detect for the first time exoplanets. The interest of high contrast, of imaging exoplanets and using chronograph is that we already know where the planet is, and we want to get an image of it, and we want to get photons of it, and we want to have information and spectra out of it. So I imagine a chronographs that is built so we can put a spectroscopy behind it.
Right.
And we already know where the planet is. We don't need to look for an exoplanet. We just want to put something.
Right. But with spectroscopy, you need a fairly bright image of the planet. You need a lot of light. So do you think that 6 meter telescope is big enough? Or do you think to get that to do the spectroscopy, you would need a bigger telescope?
One of the main drawbacks of the chronograph are these dark areas here. We have a loss of photons coming from the planet that are stopped by those dark areas. And if we have a chronograph that is following the planet, that is not trying to remove the starlight everywhere, we just remove the starlight where the planet is, then we have less photons that are lost. We can get more photons just using this method. Do you understand what I mean?
Mm-hmm. Yep. So, okay. And getting that spectra, what would you be observing? I mean, I guess you would be observing the atmosphere, the gases in the atmosphere of the Earth-sized planet around the sun-like star. Is that?
Yeah. So what we are looking for in general are biomarkers, because we are trying to look for life somewhere else. We don't know how to get it, but we know how to get some clues that it could maybe perhaps exist on a planet. So we know what to look for. We have this kind of cocktail of biomarkers, of molecules we are looking for, including the carbon dioxide, carbon derivative molecules in general, water, oxygen, and ozone. I don't know. Ozone? Is it?
Ozone, yeah.
Okay. So all those molecules we are looking for, and this is mainly located in the near infrared and mid-infrared, and a bit in the visible. So I would say also my perfect dream telescope will also look for a bit like Webb in the visible, in the near infrared and in mid-infrared.
Right. So you do want that wider field of view, not just visible. You want to see, there are other things potentially, like there's been this idea that, say, plants reflect infrared light in a very specific wavelength of infrared. Mm-hmm. They call it the red edge. That might be interesting if you could detect that with your telescope. I mean, the biosignatures one is actually very difficult. I mean, astronomers are arguing right now about if there even is a biosignature that would tell you that there was life there. There was like a paper that just came out proposing nitrous oxide as a chemical. But then you think about the search for life on Venus, and astronomers are arguing about phosphine, and Venus is right there. It's like right beside us, and yet we can't be certain if the chemicals of life are there. So it sounds like a tricky job to detect life. You could find carbon dioxide, methane. All of these have natural processes that create them as well.
Yeah, that's very, very true. We already don't know what is happening in our system. So even if we have some ideas of what would be happening somewhere in another system, what we cannot know for sure. And I think that's also really beautiful, actually. And it's also why it's important to say that even if we discover an Earth-like planet somewhere, we cannot be sure life is happening there. We cannot be sure. We know we will not go there, and we know there is no planet B. Currently, we don't find out a planet B, and even if we find one, we don't know. We cannot go there, and we don't know what is happening there.
Well, so we evolved on Earth for this environment. This is the best planet that we will ever find in the universe because we're part of it. So,
we know life is happening here. Let's protect it.
Right. We can't be sure that intelligent life is happening here, but we do know that life is happening here. So then what interesting result should people be watching for from you and your team next? Like, what's the thing that we will see in the next few months or maybe year that is the result of the work that you're doing right now?
So in the coming years, there will be the setup of the ground-based giant telescopes. And they will have very powerful chronographs. And some of them they're large enough to optically resolve large planets around faint stars, I would say. This is something we can look for. This is really, it will be really interesting. So it will be around 2027, 2028. So that would be a nice result to see what is happening there. Yeah, I would say.
2028. I mean, I guess 2020 around that. And Nancy Grace Roman launches around that same time as well. Yeah. So I think if people will see, okay, the 40-meter extremely large telescope works and is starting to show pictures of exoplanets. Nancy Grace Roman is flying and testing all of this next level technology. And then we will see those come together in the one that will find another Earth.
Yeah. And those telescopes will have up-to-date technology. And this is really good. Like first ground-based telescope are more able to get up-to-date technology because they are ground-based. And also the Nancy Grace Roman Space Telescope will have very powerful technology on it. I think, those two, 2028, 2030 maybe is the time to set up and all of that will be a very nice time.
It's just around the corner. It'll feel like you won't even notice, and suddenly these next telescopes are online and taking these images. It's really exciting, and I'm really looking forward to seeing these next telescopes come online. I mean, I always say that we're in the golden age of astronomy. It always feels like we're, because of all of these amazing instruments, but when those come online, that is just amazing what's going to happen next. Well, it's been a pleasure talking with you today. What is the best place for people to keep track of the work that you're doing and interact if they want to?
I would say Twitter I'm quite active on Twitter, mainly in French, but sometimes in English, and I can still be contacted to talk English. I still have a very strong French accent, but, but
you
I
did
can
great.
understand.
Again,
So
your French is, your English is better than my French. Très bien. And what's your Twitter handle?
Lucie Leboulleux, like my first name, my family name,
Yep.
all together.
Okay.
And I'm under the name Lucie in the Sky, I think, or in the stars.
Okay. Wonderful. Yeah. Well, Dr. Leboulleux, thank you so much for taking the time to chat with me today. It was absolutely fascinating. Great to sort of update my understanding of coronagraphs and the current state of the art. I really appreciate it. And good luck with the work that you're doing. And I can't wait to see this adaptive coronograph technology actually functioning. It sounds exciting.
Thank you very much. Thank you for putting attention to technology also.
Yeah, absolutely. All right. Take care.